Hello and welcome to the 11th session of the LSST-DA Data Science Fellowship Program. This is our first ever virtual session, and so we hope that you enjoy the content that we're providing in this new format. This is very new for all of us, obviously, and we certainly hope that we could be meeting in better circumstances, but given the ongoing situation, this is how we're going to proceed for now. Given that all of this is new, that means that there's probably a lot of kinks that still need to be worked out. So we will be providing all of you with feedback forms at the end of the session, and we hope that you can sort of take notes as you work through the lectures and you work through the notebooks in order to provide us feedback on terms of what does work, what doesn't work, what can we change moving forward in order to improve the program. Because as much as we would love to see all of you next week if we could, it seems likely that the next session after this one is also going to be held in a virtual format. Now, before we really dive in today, I know that the big question on all of your minds is, if no one is in the room with Adam while he gives the lecture, is he still going to make terrible jokes? And the answer to that question should be obvious. Absolutely. Absolutely I am. In fact, let's start with one right now. Even though I'm recording both of my lectures back to back, I have changed my outfit and the way that I appear to give the illusion that time has passed, much like it would during a normal session where I'm giving a talk on the first and the last day. So beyond that, as I said, this will be a virtual session. Talks will be recorded, and then we're expecting you to work on the notebooks thereafter. As is typically the case, I'm going to try to introduce this session and provide an overview of what it is that we'll be going over. So my talk is Photons Aren't Science, and what are the challenges of turning the former into the latter. So session 11, the one that we are about to embark on, is primarily focused on image processing. Informally, we're essentially asking the question, what happens between the glass and the database? And what I mean by that is the following. When most people imagine the Reuben Observatory, they probably immediately conjure some image in their head that looks much like the one on your screen, right? We're talking about some giant, modern, very fancy telescope dome with a large 8-meter piece of glass inside of there. There's a connected facility that both has a lot of computational power for controlling the telescope, taking the data, sending that data back to the data centers in the United States, as well as a gigantic lab where they can repolish the mirror if necessary, or work on the camera, or update the filters. So, giant monolithic survey facility on top of a mountain at Cerro Photons in Chile. But in reality, almost none of us, are ever going to actually visit the Reuben Observatory. Really, our interactions with the Reuben Observatory are going to look more like the image on your screen now, right? There's going to be some large database. That database is going to have a bunch of measurements in it, and those measurements on basically every source that's been measured and every individual image taken over the course of 10 years of those sources, right? What are the fluxes, etc. All of that's going to be in this database, and that's how we as a community are going to interact with the Reuben Observatory, right? Much like interactions with the Sloan Digital Sky Survey or Pan-STARRS, Dark Energy Camera, etc. Right? So given the impending deluge of data from the Reuben Observatory's Legacy Survey of Space and Time, or LSST, you could make the argument that you only really need 2 skills to be a successful scientist in the 2020s. The first one being an advanced knowledge of programming, right? So can you hack things with Python? Do you know how to get into a database, extract information, extract it in a clever and quick fashion? Can you parallelize software that would be too slow to run on a single processor, etc.? So programming skills. And then also some knowledge of statistics, right? Can you build a machine learning model to understand what's going on with the 10 million stars that meet some criterion within the Reuben Observatory database? Or if you're trying to build some very specific inference, like what is sigma 8 within the universe, or the length scale for baryon acoustic oscillations, right? Can you build some Bayesian model where you have the appropriate likelihood and prior and shove all your data into that to run an MCMC to get some answer to that question, right? And so those two skills, programming and statistics broadly, may be all that you think you need to succeed in an era where all of us are just working with numbers out of a database. And those two skills are the precise reason why we have you here as part of the DSFP. We want you to master them and become full-fledged practicing data scientists, right? That is what we are hoping to teach. Okay, but if you want to make that particular argument, the argument that all you need is some hacking skills and some stats skills, you're missing an essential ingredient, and one that if you do not have, I contend, you will not ever actually provide meaningful scientific breakthroughs. And that is substantive expertise in the field that you care about, right? So here's a Venn diagram sort of showing us where data science sits. And it sits in the middle, right, of in the middle of ideas and knowledge of hacking. So this includes, right, can you build some Python script? Math and statistics knowledge, right? So without that, of course, you cannot do any research. And then substantive expertise, right? Do you know what's going on with the actual data that's been collected in your field? And it's for this reason that I've actually never been particularly worried about losing my job, even though there are many, many, many people out there that are far better at programming than I am, and far, far, far better in terms of their understanding of both mathematics and statistics, okay? But those people don't understand astronomy, and I do. And that's the huge advantage that all of us have when it comes to understanding what has happened with the data that's coming from the Reuben Observatory. Domain knowledge is essential. Okay? And I said this, but I want to just repeat it again, right? I think a lot of times within the DSFP, we all maybe get down on ourselves, and I'll be honest, this happens to me too. We bring in guest lecturers that know far more than we do, and they start talking about some topic, and it's just very hard to understand the first time you've heard about it, okay? But those people, right, not everyone that comes in and does that has the same domain knowledge that you do. So I want to try to prove that this is the case, prove that a data scientist cannot just grab the LSST database and somehow destroy all of us when it comes to making astronomical or astrophysical discoveries over the next decade. Okay? So let's think about some conclusions that you might draw if all you had access to was the Reuben Observatory database and you didn't really know any astronomy, right? Or how the DOE LSST detectors work, right? Those two critical ingredients being our specific domain knowledge. All right, so one possible conclusion that you would draw from looking at the database is that there are no galaxies, not a single galaxy that's fainter than 27.5 magnitudes in the I band. Okay. Well, what would this mean? I mean, if there's no galaxies fainter than that, that could mean that you've actually discovered the edge of the universe, right? Nothing's fainter. That must mean that there's nothing else out there. Okay. Now, that incorrect conclusion, and it's a very incorrect conclusion, follows from the inverse square law. We of course know that the flux that you detect for any individual source is inversely proportional to the distance to that source squared. And if you combine that with the sensitivity limit of the LSST detector, there's going to be sources that are, simply put, too faint to be detected. Either they are too far away, or they aren't so far away, but intrinsically they're very faint, right? And so we'll be missing both of those. And there's no way that with an optical detector you would actually be seeing out to the, quote, edge of the universe, right? So that one's a bit silly. Let's maybe get a little bit more complicated. So suppose you just want to find what are the two closest stars within the Milky Way. And if you're just using the LSST database to do this, you would actually find that the two closest stars are about 0.35 arcseconds apart. Okay. Well, why might that be? Well, I suppose if the two closest stars you could possibly get are 0.35 arcseconds apart, that might mean that there's some sort of repulsive force, right, that prevents two stars from ever getting closer than that particular distance, right? That sounds like a Nature paper. We should definitely write that one. Right? So clearly this is wrong, right? And that conclusion, that stars cannot be closer than whatever that limit is for LSST, is just a reflection of the typical atmospheric conditions at Cerro Pachon. So the typical seeing, right, the typical sort of atmospheric smearing of the point spread function on an image is going to be on the order of 0.7 arcseconds. Because that is the sort of typical resolution that you have, that means that we will not be able to resolve stars that are closer than about half of that, right? So any nearby stars, any two stars that are very close together, so a apparent separation of less than 0.3 arcseconds or so, will not actually be resolved by LSST. And so with LSST alone and the LSST database, you would not ever be able to see those two stars that are close together, right? And that's something that you only know if you understand how the observing system works. Okay, let's try something even more complicated. All right, so if you add up all the flux in the database in the R band, it will be more than all of the flux in the Y band. So we're talking about, roughly speaking, 6,500 angstroms versus 1 micron. Okay, so that means that the universe is actually very red because there's more R band light. So what does this mean? Let's think about this. So red is the color of the Chicago Bulls, and the Chicago Bulls had the greatest basketball player ever, Michael Jordan. So the universe is trying to confirm something that some of us already know. Right, okay, that's obviously ridiculous. That's not what's going on. So this conclusion, right, that there's more R band light than Y band light in the universe is a little bit more subtle than the first two examples. And there's a few different factors which we'll go over now. So LSST itself is going to be more sensitive in the R band than it is in the Y band. And the two main reasons for this is that the sky backgrounds are lower in the R band, and this detector itself is more efficient at 6,500 angstroms than it is at 1 micron. So those two factors together means that in a fixed exposure time, you will see fainter sources in the R band than you do in the Y band. Right? So now when thinking about the universe as a whole, any blue sources that you have naturally emit more light in the R band than the Y band. So if you sum all those up, you'll get more R band flux than Y band flux. But that should be countered by the fact that most of the observed sources by LSST should be red, because there's dust, which is shifting the colors of everything towards the red, and also all of the galaxies and quasars that are seen at higher redshifts, right? The redshift is also shifting the colors of those sources to the red. So if there are more red sources than blue sources, we might expect for there to be more Y band light. But a lot of these red sources will only be detected ultimately in the R band filter. And that is because of the relative sensitivity in the two detectors. So that means that when you add those with the blue sources compared to the red sources that are detected, what you're going to end up with is a situation where you have more total R band flux than Y band flux. Okay? So this is subtle, and it requires an understanding of the telescope system. Okay? So the upshot here is that no computer scientist is going to show up and sort of immediately put us out of the job, which is good news, right? Domain knowledge of both astrophysics, right? You need to understand the physics of what you're trying to study, but also critically, the full telescope system is an essential ingredient for success once the Reuben Observatory begins LSST. Right? LSST is going to push the boundaries of what you can actually do in terms of a ground-based wide field survey. And we're going to really have to apply our data science toolbox in order to optimize the science that we get out of LSST. So that means that you're going to have, as we said at the beginning, substantial working knowledge of both hacking, right? You cannot be successful with the billions of sources catalog in LSST without a good sense of how to write programs. And you're going to need stats and mathematical analysis, right? The skills that we are teaching as part of the DSFP. But if you don't have a corresponding expertise, both in the astrophysics of what's happening in the universe and how the data were acquired, essentially how the telescope system works, then you're going to be at a real disadvantage. And that is why we are trying to build a holistic picture. And that is largely our focus this week. So this entire session, as I said at the beginning, is going to be on image processing, and we're going to be trying to figure out, with wide field images, how do you go from photons landing on some large dish of glass to eventually a nicely sorted and ordered database where you have a bunch of flux measurements and position measurements and other information that you may care about in order to extract the science that's meaningful to you. So that brings us now to telescopes. Mostly we'll be talking about detectors. We will also talk a bit about telescope systems today. And throughout this session, I just want to provide a quick, brief overview. So let me start with a true story. When I was in grad school, I got together with a couple of friends of mine, and we designed and developed a new telescope, which we called the Imaginary Telescope. And let me tell you, I have seen a lot of plans for telescopes, but the IT is awesome, and it is definitely the best, right? So the IT has a diameter of 1 AU. It is huge. And not only that, it detects every single wavelength within the electromagnetic spectrum with 100% efficiency. There's no losses. Giant piece of glass, no losses, every single wavelength. It's amazing. This telescope is particularly revolutionary in its design, and as you can imagine, once we get the money to build this, it's going to serve as a complete game changer in the field of astronomy. Okay. So why is this important to have 100% efficiency in a huge piece of glass? Well, fundamentally, the thing that we care about in astronomy is measuring fluxes. And to some extent, we also care about measuring positions, but these two measurements, as we'll see over the course of this session, are related, right? In principle, a flux measurement is very straightforward. All you have to do is count the number of photons from a source per unit energy per unit time. Boom, then you're done with your flux measurement. If you want to be more sensitive to faint fluxes, all you do is increase the size of your telescope. And indeed, this is why I'm here pitching to you today the IT telescope. So I hope you go home to your home institutions and tell your department chairs that they should provide funding for the IT telescope. Okay. So in practice, however, right, while the problem is simple, we just want to count the photons per unit energy per unit time, there are a few things that make life a little bit more complicated. So unlike the IT, actual telescopes that have been built so far have optical elements that are not 100% efficient, right? So maybe the mirror doesn't actually reflect every single photon that's incident on it. Maybe by collimating the light and focusing the light, you lose some of your photons. Maybe when you put a filter in your optical path so that you can collect R-band light or Y-band light, that filter is not 100% transparent to the photons that you care about. Right? All of these things mean that your telescope is not 100% efficient. Now, fortunately, all of those things I just described, every single one of those issues, we can measure, typically with very, very high precision. And so because we can measure those things with high precision, we can correct them. Right? Now, if you want to be very, very careful, this still complicates things relative to the simple problem of counting, because the uncertainties move beyond basic Poisson at that stage. It's also the case that our detectors introduce noise to our instruments, right? So typically for something like the CCD that we're going to use with LSST, we will cool the detector, and that will sort of keep the thermal noise in the detector at a low value, a value typically that's so low that it doesn't particularly affect our measurements. But nevertheless, the detectors themselves add noise. So it's not just simple counting anymore. We have to account for that, right? One that's very difficult is that our detectors cannot continue counting forever, right? So this has to do to the analog-digital conversion that happens within the detectors, and we'll hear more about that from Colin. But essentially, once you get up to around 50,000, 60,000 counts, right? You've counted 50, 60,000 incident photons, your detector simply can no longer count the photons that are coming in to the CCD, right? So that's an effect that's known as saturation, and it means that the dynamic range of any particular image that you take is going to be limited. So the very brightest source for which you can reliably count the number of photons is going to be set by your exposure time, and anything brighter than that, you're not going to be able to get a very good measurement of how bright the source is. Right? There are other issues as well. So the incident photons into the detector, we cannot perfectly measure their positions. And if you want to know, right, exactly where a particular star is located in the sky, you need to know its position on the detector quite well, right? But the Heisenberg uncertainty principle means that we cannot measure this perfectly, right? We also know that the incoming waveforms, after things have been transformed through the optics of the mirror, are going to be a sort of continuous, smooth pattern, right? That's what the actual genuine point spread function looks like, something that's smooth. And yet our detector requires us to use pixels. So we're taking a continuous signal and we're discretizing it, right? And that creates some problems. Again, we'll hear more about that from Colin. And then here's a subtle one, and one that I didn't even appreciate until well after I was out of grad school, right? But every camera has a shutter, right? And the shutter opens and the exposure starts, and then the shutter closes. Now, at the very center of your focal plane, as the camera opens, right, light starts to hit the detector, but towards the edges of the focal plane, until the shutter is all the way open, that incident light hasn't come in, right? So that actually means that depending on what pixel you're looking at within a detector, right, the exposure time is actually going to be variable, right? So that's a subtle effect, but nevertheless, if you want to be very, very precise, if you want to measure fluxes absolutely to the very best of your ability, that is something that you need to account for as you are counting what's happening in the individual pixels of your detector. Okay. So in summary, we have a very basic task. We want to count all of the photons, right? But measuring the flux and position of an astronomical source is actually somewhat complicated, and this is what we're going to dive into this week. Okay? We do control all the elements of the telescope system, though, and we can make a variety of different measurements to correct for things like inefficiencies in the optical elements or the instrument itself. Okay? But there's one super important thing that we cannot control. Clouds. Clouds, 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 clouds. Clouds are the worst thing ever. Unless you're having a lazy afternoon, a picnic, you're looking up at the sky, then clouds are great. But for astronomers, clouds are the worst thing ever. Okay? The atmosphere just complicates everything about what we're hoping to do, right? We just want to count photons. All we want to do is count, right? But calibration is really, really challenging. Some effects like turbulence, which distort the signal, right? That makes life harder, but the real pain is the clouds. On any given night, you cannot be absolutely sure whether or not there are clouds present when you're collecting data. Okay. So we have a way to get around this. We have a scheme for this. Briefly, right, very basically, if we want to calibrate how many photons we've counted on any sort of individual image, this is how you go about doing that, okay? So first and foremost, all of us, right, so you, me, everyone that's watching this lecture, we need to agree that there's some small handful of stars that are not variable, and between you and me, we know that all stars are variable based on the data that we've gotten from the Kepler telescope and SOHO and TESS. But what we're saying when we say that they're not variable is that to within the precision of whatever instrument we're using, the star is not variable. And that said star has a precisely known flux. Okay? So if we all agree that that's true, then what we can do is we can take observations on nights that are photometric, okay? And you should see me doing the air quotes there because there isn't actually a genuine definition of what it means to be photometric. That's just something that, again, we all sort of agree when things are or are not photometric. And then we observe the standard stars, which aren't variable, but secretly they're actually variable, right? And any other source that we care about. And we make some basic assumptions about attenuation that might be happening in the atmosphere depending on the angle of your observations, right? And so finally, we can compare the counts for the source we care about to the counts that we get from the standard stars where we know the flux, and that essentially creates a mapping from counts to flux, okay? So that's the basics of classically how you might calibrate your images. There are some more clever techniques, and this sort of rough strategy doesn't necessarily work very well for a wide field survey, but luckily we have Dr. Colin Slater who's going to tell us more about that later in the session. Okay? All right, so from the beginning, all we've really been focusing on is how do we measure a flux? And we know that the answer is simple. You count the photons, right? Okay, but before you can ever even worry about measuring the flux of a source, you have to find the source in the first place, okay? All right, so let's all do that now together. How many stars are in this image? Now I'm going to pause for a second. In fact, I'm going to do it myself. So just count how many stars you see in this image. Okay, I'll wait another second. Okay. So I'm going to guess that you identified 23 stars in that image, right? And I'm going to guess that the way you did that is by eyeballing a rough background level in the image and then looking for individual peaks above that background. So algorithmically, that is exactly how you find sources in an image. You essentially define a background and then look for peaks. Peaks tell you where the sources are. Okay. Now, let me ask the same question for this image. How many stars, or actually most of these things are galaxies. So let's say, how many sources total do you see in this image? I'll pause, I'll give you a chance to count. Okay, clearly I'm being ridiculous. There's no way that you can count everything in here, particularly in a short amount of time. Let's make this a little bit easier. Let's zoom in on a single region, and let me ask, how many sources are in this image? Okay, again, I don't care about actually counting what you see here. The point is, this particular image is taken by the hypersupreme cam, and it reaches a depth that's comparable to the full depth of LSST. And what you'll see is that in that image, right, nearly anywhere you look, there is a galaxy. Every single pixel, there is a galaxy. Okay. So going back to our simple idea of defining a background, how do you actually define a background when there are literally galaxies everywhere, right? What pixels are just background? This is actually a really hard question, and in fact, many would argue that it's an unanswered question. Fortunately, we have Dr. Yusra Al-Sarad, who is going to tell us more about that later this session, right? Similarly, let's go back to the image, right? How do we assign which photons, right, in a given pixel belong to a single source, right? So here I see what looks an awful lot like a galaxy, but then kind of overlapping with that galaxy is two blue things here. Those look like stars. And that means we're getting light from multiple sources in the same pixel, right? How do you do that? How do you decide which light should be assigned to which source in that case, right? This is also a challenging problem that, again, Yusra will tell us more about later in the session. Okay. All right, so let's try something that's a little bit easier, a little bit more straightforward. Suppose I want to measure the flux of a galaxy, right? So I look at an image, I say, right there's a galaxy. I want to know what its flux is. And there are several different reasons why you might want to do that, but one is that if you know the luminosity of a galaxy, that can tell you a lot of information about its mass, say. Okay? If you measure the flux in multiple filters, so you have a color, maybe you can learn about what's happening with any dust that might be present in the galaxy, or whether or not it's actively forming stars. And if it is forming stars, how active is that star formation? Okay. All right, so simple question. How do we measure the flux of a galaxy? On the next slide, I'm going to show you a galaxy. I want you to just take a few seconds, make a quick mental map while looking at the galaxy. Which pixels within the image belong to the galaxy? So in short, which pixels should we add to our count as we try to determine the flux of the given galaxy? So here we go. And there's two axes there, so maybe just make a short note of sort of the rough extent of the galaxy based on the pixel numbers. Okay? All right, so now I want to do the exact same thing, okay? Looking at a new galaxy, different galaxy, all right? Okay, so which pixels are included in this case? Just make a quick mental note in your head, all right? Okay? All right, and we're gonna do it one more time. So we've done this for 3 different galaxies now. One more time, I want you to look at this galaxy and figure out which pixel should be included. Okay, now you may have realized this as we were doing this, but I just showed you the same galaxy 3 different times. And each time, the only thing I changed is the stretch, essentially the relative intensity of the individual pixels to each other. Okay? Now, despite showing you the same galaxy 3 different times, I would guess, and this is what I did, that you expanded the number of pixels that you would have to count for each galaxy, right? So that brings us to a tough question. How do you actually define the edge of a galaxy? This is something that Professor Gary Bernstein is going to answer for us later this session. Okay. And of course, you need to define the edge of the galaxy if you want to add all the photons together that contribute to the flux from that particular source, right? This is a hard problem, all right? Fortunately, we have an expert to tell us more about it. Okay, so without going into all the gory details, which we will before the session is over, right? Our simple problem, count some photons and then measure a flux, is actually very, very complicated. Now, some of these things can be understood pretty simply, pretty straightforwardly, right? We can determine the sensitivity of the detector with high precision, right? But the number of clouds and precisely how much light they're attenuating, that's very difficult to measure. Okay. So that brings us to breakout problem number 1. So given all of the complications that we have in the telescope system, how can you actually make any informed inferences about the universe, right? As a hint, I'll tell you to think back to the previous session. Okay, so now what I would like for you to do is pause the lecture and just take a few minutes to think about your answer. I'll just sit here and wait. Okay, you can hit pause. We'll move on in a second. Okay, welcome back. All right, so normally we like to have a discussion here. I know we cannot do that in this case, so I'll just jump ahead to my solution, right? So given all these uncertainties and things that are difficult to quantify, Bayes gives us an amazing solution, right? We could write down a likelihood function that parameterizes every single thing about our telescope system, right? What's the noise in the detector? How many clouds are in the atmosphere? What is the angle of the observations? What is the efficiency of our individual filters, right? What is the time-dependent emission of the galaxy that we've been looking at for 10 years, right? All of that can go into our likelihood function, and then we could run a giant MCMC. And what we're going to do is integrate the posterior. We marginalize over every single thing that we don't know or don't precisely understand. Like, who cares how many clouds there are? We're just going to marginalize over that, right? And as a result, we can answer any question that our heart may desire. What's the BAO length scale? What's the 2-point correlation function? What's the rate of supernovae as a function of redshift, right? Okay, that's great. That is the solution, right? But, speed matters, right? There is not a single computer or collection of computers on the entire Earth where you could build a likelihood that describes every single photon that has ever been incident on the LSST detector, and then sample from some posterior in order to make some sort of inference. Okay. So as a result, we have to make some shortcuts, we have to make some approximations, and not everything becomes Bayesian within our analysis. That's okay. Just to give you a sense of how this matters, we're going to get to breakout problem number 2. So I want to know, how long would it take to perform basic processing of all of the Reuben Observatory LSST images on your laptop? So the bare minimum for image processing, as we'll hear more about later, includes bias corrections. So this is basically subtracting the bias charge that's on every detector, and then flat field corrections to correct for intrapixel sensitivity differences, right? So that essentially means you take your CCD image, you have to run a subtraction on every pixel, you have to run a division on every pixel. So if you assume that your laptop has a single 3 gigahertz processor, and it requires 1 tick to perform a single addition operation and 4 ticks to perform a single multiplication operation, how long will it take you to run all of LSST? Okay? So once again, pause the lecture and take a moment or two to think about what the answer is here. welcome back. So I hope you're able to work out an answer. Here's the solution I came up with. And one thing I'll note is that a lot of the numbers in this particular solution are things that you should commit to memory, right? Remember, as DSFP fellows, you are ambassadors for the Reuben Observatory and for our program. And so people will come to you with questions about what's happening with the observatory or what's happening with the observations. And so many of these numbers are things that you should just sort of know, right? Okay, so first and foremost, we know that the detector has 3.2 gigapixels, and 3.2 gigapixels will need to be processed for every field that is observed and every observation. We know that a single field covers about 10 square degrees, and that the Reuben Observatory is going to survey the entire southern hemisphere. So the full sky is about 40,000 square degrees, so if you're doing just half, you have 20,000 square degrees. We said that addition takes 1 tick, multiplication takes 4, so that means every pixel that we're going to process is going to require 5 ticks on our processor. And then we also have a 3 gigahertz processor. And then finally, we know that every field within the footprint of the Reuben Observatory, LSST, is going to be observed about 1,000 times, right? So the key numbers, things to remember, 3.2 gigapixels, 10 square degrees, 1,000 observations per field, right? If you multiply all these numbers together, you get approximately 4 months. Well, so that's not such bad news, right? If you had a project that had to run on your laptop and it took 4 months, you could do that, read some books, read a few papers, come back 4 months later, and still have several years left over to finish your PhD thesis, right? Okay, but this is the most basic operations possible. A more realistic solution here is, based on the Palomar transient factory, it takes roughly 30 seconds to fully process an image. So I mean bias and flat field, as we talked about a second ago, but then also, right, once you have your image, you want to solve for the astrometry, you want to know where every X and Y pixel, how that corresponds to some position on the sky. You want to measure photometry, right? You want to actually get the fluxes of everything that you've looked at. You might want to do image subtraction if you care about finding things that are changing or variable in brightness. So PTF, doing all of that, 30 seconds for 1 million pixels. And I'll also note, a lot of that is tied up in I/O, right? So you have to take the pixels, you have to put them in memory, perform all these operations, and then write that back out so you know what happened, okay? So if we use the same numbers from the previous problem, what's the total number of pixels that need to be processed, LSST is going to take 200 years. Raise your hand if you want to be in grad school for 200 years. I miss grad school. Okay. Clearly, that is unreasonable. Now, fortunately, the solution in this particular case is that we can take the individual CCDs, the individual images from LSST, and we can process them at the same time, right? So using a supercomputer, you can actually parallelize all of these operations, and the spec right now is that all of LSST should be reprocessable, basically from raw images, what came off the telescope, all the way to information that goes into the database in 1 month's time, okay? So that is the power of parallel computing, which I know we haven't taught all of you about, but we will get to that in a future session, I promise. Okay, so in conclusion, most astronomers will only ever interact with the Reuben Observatory via the LSST database. Okay? So the database is going to be key. Nevertheless, domain knowledge is going to be essential. If you don't understand astrophysics, if you don't understand how photons turn into numbers that are in the database, right, you're going to be hindered and you're going to be unable to make really, really pressing and valuable insights over the course of the next decade, right? And as we will see over the remainder of this session, lots and lots and lots of complicated analysis happens between the glass where the photons are incident and the database, okay? And with that, I will pause and take your questions. At least I will take your questions during our virtual meeting whenever I see you in the next few days or few weeks, depending on when you watch this. Thank you, and good luck working on the first notebook.